Hey everyone, and welcome. We're surrounded by electricity, right? We use it every single day. But have you ever stopped to think about what it actually is? Well, that's what we're going to do. We're going to pull back the curtain on this invisible force and look at the very things that control it, what lets it flow and what stops it cold. So let's just start with a really simple question. Think about it. When you flip a light switch or plug in your phone, what is really happening inside that wire? What's actually moving through there? I mean, what's going on at a level so small we can't even see it? And you know what? The answer is kind of simple. It all comes down to this. Electric current is just a flow of these super, super tiny particles called electrons. That's it. The easiest way to picture it is like water flowing through a hose. But instead of water, it's this massive river of electrons on the move. Okay, so if these electrons are flowing like a river, they obviously need a riverbed, right? They need a path to follow. And that brings us to our first huge concept, conductors. These are basically the highways that let the electrons travel. Yeah, that path is called a conductor. And a conductor is just any material that makes it super easy for electrons to move through it. It's like it just rolls out the red carpet and says, come on through. It is literally the superhighway for electricity. But here's the cool thing. These electron highways aren't just the metal wires you're thinking of. Not at all. Conductors can be all sorts of things, like certain liquids or even solids that have what we call low resistance. Now, resistance is just what it sounds like. It's how much a material tries to stop that flow of electrons. So low resistance means an easy ride. And get this, even some gases can act as conductors, but only under some really specific conditions. All right, so if you've got these superhighways, it makes sense that you'd also need some walls, right? Some roadblocks to control where all that traffic is going. And in the world of electricity, we call those insulators. An insulator is the polar opposite of a conductor. Its whole job is to block that path. It just stops electrons dead in their tracks. It's got really high resistance, so it basically throws up a giant stop sign and tells that electric current, nope, you're not getting through here. And you see these everywhere. A perfect example is the air around us. It's actually a fantastic insulator. That's a good thing. Another one is any solid with high resistance. Think about the rubber or plastic that's wrapped around an electrical wire. That's the insulator doing its job. So you see the split, right? It's really clear. Conductors are the highways with low resistance, letting electrons zoom by. Insulators are the roadblocks with high resistance, stopping them completely. And it's this simple back and forth, this push and pull, that lets us control electricity and use it safely. All right, so we just said that most gases are insulators, right? The air around us, for example. But what if I told you that's not the whole story? What if some materials could, I don't know, switch sides? And this is where things get really, really cool. Our source material points out that if you take a gas, stick it in a sealed tube, and drop the pressure way, way down, it suddenly becomes a conductor. How wild is that? It just goes to show that these labels, conductor, insulator, they're not always permanent. The right conditions can totally flip the script. So that naturally leads to a bigger question, doesn't it? What else can affect this flow of electrons? As it turns out, there are four main things that can make that electron's journey either a smooth ride or a really tough one. Okay, so the source lays out four key factors. First up is the length of the conductor. Simple enough. The longer the wire, the more resistance. Makes sense. Second is its cross-section, basically how thick it is. A thicker wire is like a bigger highway with more lanes, so there's less resistance. Third is the material itself. I mean, some materials like copper are just naturally amazing conductors. And last but definitely not least, and this one is super important, is temperature. Now, this is the part you really want to pay attention to. There's this quote from the source that's just critical. It basically says that any insulator can lose its insulating powers if it gets too hot. Think about that. It can stop being a roadblock and turn into a highway, letting electricity go places it absolutely should not be. And that is why this all matters in the real world. That plastic coating around a wire, that's our insulator. It has to stay relatively cool. If it gets too hot, it can fail. That protective barrier just breaks down, and suddenly you have a massive safety problem. This isn't just theory. It's the core science behind almost every electrical safety rule out there. So let's leave it with this thought. We've just seen how something as simple as temperature can completely flip the switch on a material's basic properties. It really makes you wonder, right? What other invisible forces, what other hidden rules of the game are out there shaping how energy moves all around us? just waiting for us to figure them out.